Okay, so we're going to continue on nomenclature. I think we had done alkanes, haloalkanes. Let's do alkynes. So if I have, let's say, that compound, so that's an alkyne, so I'll write yne. Check the longest carbon chain, that in this case, of course, includes the alkynic function or the alkylating function. So I have 1, 2, 3, 4, 5 carbons. So that's pentyne. And we need to indicate where along the carbon chain the triple bond is, because that, of course, is one of many pentynes, right? I could have had a triple bond between carbons 1 and 2, which I have here. It could have been between, it could be between carbons 2 and 3, so carbons 1, let's see, so 1, 2, 3, 4, 5, 6 is one more. So it could have been here between carbons 2 and 3. So the different pentynes. I need to indicate where along the carbon chain my triple bond is. And like with the alkenes, because the triple bond spreads over 2 carbons, I can't give it 2 numbers. I can't give 2 locus. So I'll pick a smaller number, right? So I'll call this compound 1 pentyne, or I can call it pent 1 yne. Similarly, I will call this compound as an alkyne. So I'll write yne. I've got 1, 2, 3, 4, 5 carbons, so that's pentyne. And the triple bond is between carbons, so I want a smaller number, so obviously I'm going to number from right to left, right? So carbon 1, 2, so I'm going to call this 2 pentyne, or I can call it pent 2 yne. If I have substituents along the alkyne, if I have something like this, something like that, okay. I want to get, again, this is going to be an alkyne, so I'm going to write YNE. I want to get the longest chain that includes my functional groups. So that's going to be carbon 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be an octyne. It's not just an octyne, right? So if I pick this, of course, it's my longest chain, right? And I'm doing this sort of mentally in my head. Then it's not just octyne, it's got 2 chlorines and a methyl, and C for chloro precedes M for methyl in the alphabet. So this was on the 2 chlorines, so this is a dichloro methyl octyne. So I need locants. I need locants to indicate where the chlorines are, where the methyl is, and where the triple bond is. So again, I want to give the major functional group the lower locant. So if I go 1, 2, 3, 4 is where 1, 2, 3, 4 is where it starts. 1, 2, 3, 4 is where it starts. So regardless of which direction I go in, the alkyne is going to have a number 4. So that's good. So I'm going to try to get then the lowest sum of the others. So I've got 2 chlorines, and obviously if I number from this direction, I'll have 2, 2, and then this is going to be on carbon 6. So 2, 2, 6, right, will be better than 1, 2, 3, 7, 7. So I'm going to call this then, I'm going to number from right to left, because the triple bond doesn't care. It's 4 either direction. So I'm going to go and try to get the lower sum for the other groups. So that's going to be, it's 2, 2, dichloro, 1, 2, 3, 4, 5, 6, 6 methyl, and I'm going to say it's 4 octyne, or 2, 2 dichloro, 6-methyl, oct, 4-ine. When we name, for example, alcohols, what we call an alcohol is all, and then I'm going to try to get the character of, and I think yes, we had started talking about this a bit in fact. We're going to try to get the character now of the carbon backbone. So when we name alkanes, alkenes, alkynes, right, we would have ine as the base name for alkynes, ene for alkenes, ane for alkenes. When we are looking at alcohols, we put all for the base name, but then we also want to try to get the character of the carbon backbone. In other words, is the carbon backbone saturated? In other words, so saturated means that there are only carbon-carbon single bonds. If they're carbon-carbon double bonds or carbon-carbon triple bonds, it is said to be unsaturated. Okay? In other words, it's missing H's, basically. So I will now have to indicate, is my carbon backbone saturated or unsaturated? Right? And basically what I'm asking is, does it have, is it sort of like an alkane, an alkene, or an alkyne? Right? Are they triple bonds, double bonds, or single bonds? So if they're only single bonds, I'm going to say, so I'm going to write all for the alcohol, and then I'm going to write an, because the carbon-carbon backbone is alkane-like. So if you look at the hydrocarbons, we call them alkane, alkene, and alkyne. Okay? And all we changed was the A, Y, and N. That was A, Y, the A, E, and Y. So these are my variables. So when your compound is an alkane, alkene, alkyne, then your base name is ane, ene, ine. But when your compound is like an alcohol or an amine or so on, we end in all, and we use an, n, in to indicate the nature of the backbone. So this backbone is saturated, so I'm going to write an, all. I look at my longest chain, it's got 1, 2, 3, 4 carbons, so that's a butanol. So this tells me 3 things. This tells me my compound is an alcohol whose carbon backbone is saturated and it's got 4 carbons in the longest chain. Turns out I've got to indicate which butanol I have, because that OH could have been on this carbon, which is an entirely different compound from that one. So I need a locus to indicate where the alcohol group is, where the OH group is. And it's on carbon number 1. Again, the major functional group gets the lower locus. So this is 1 butanol, or, as you might guess from now, butan 1-ol. Okay? So 1 butanol or butan 1-ol. Not surprisingly, I would call this compound 2 butanol. Or I can call it butan 2-ol. What are the erasers? Getting erasers. So let's look at some others. Oh, what about if we try, let's name this compound. So there's several different functional groups in that compound, right? I've got the OH, I've got the triple bond, I've got the bromines and the chlorines. The one that takes priority, and I gave you guys that sheet that showed priority, is the hydroxy group of the alcohol. So I'm going to write all. I now want to know what is the character of the carbon-carbon backbone. And the carbon-carbon backbone has a triple bond in it, so this is an imol. Now I want to get the longest carbon chain, which has now 1, 2, 3, 4, 5 carbons in it. So this is a pentanol. It's not just a pentanol, it's got a chlorine and a bromine on it. So I'm going to call it a bromo-chloro-pentanol. Just for the heck of it, I'm going to change this to deuterium. Well, you know what? I'll leave this in for now. Because I already wrote that as it is. So it's a bromo-chloro-pentanol. So what I need now are locants. I want to give the OH group, the major functional group, the lower locant. So clearly I'm going from left to right. So this is carbon 1, 2, 3, 4, 5. In which case this compound is going to be, so 1, 2, 3. So it's 3 bromo, 3 chloro, pent, 1, 2, 3, 4 in 2 all. So I've got to indicate where everybody is. So I've got to indicate that the bromine is on carbon 3. And again, I separate the substituent from its locant by a hyphen. I separate information for a given substituent from information about a different substituent by another hyphen. So it's 3, I alphabetize B before C. So a bromo, 3 bromo, 3 chloro, pent, 4 in, I say where the triple bond starts, and then 2 all for where the hydroxy group is. Or I could have called it 3 bromo, 3 chloro, 4 penta. So 3 bromo, 3 chloro, 4 pentin, 2 all. So either one of those is fine. And that's sort of exactly what we did in the previous cases. What if I had something like this? If I had that. So again, my major functional group here is an alcohol, is the hydroxy group, so the compound is an alcohol. So I'm going to write all. But it turns out I've got 2 hydroxy groups, so this is a diol. What about my carbon backbone? Well, I've got 2 carbon double bonds, 2 carbon-carbon double bonds. So this is not just an N, right? Because I want to indicate what is the nature of my backbone. So it's got, so in this case where there was a triple bond, I wrote N. When there are 2 double bonds, if there's a double bond, I write N. If there are 2 double bonds, it's di-N. So this is a di-N diol. Now I want my longest chain. But again, remember, we said it's longest chain that includes the major functional groups. Because really, my longest chain goes here. 1, 2, 3, 4, 5, 6, 7, 8, 9. But if I did this as my longest chain, I would exclude both the carbon-carbon double bond and the chlorine, which out-prioritize this alkyl group. Right? Remember, the alkanes are the bottom level for our nomenclature. So I'm going to take my longest carbon chain that includes my major functional groups, which is the one that is this way. So how many carbons are in that? Well, it's got 1, 2, 3, 4, 5, 6, 7. So this is therefore a hept. And we said last day that if, as you put the length of the chain next to its the rest of the information. If you've got two consonants, you put in the letter A. So you don't say it's a heptadiendiol, you say it's a heptadiendiol. Now again, what we're doing here is we're piecemealing the information, right? We're synthesizing the information to get the name. Every little piece tells us something. Major functional group in this compound is an alcohol, is a hydroxy group, so it's an alcohol. I've got two of them. The carbon backbone is 7 carbons long and it's got 2 carbon-carbon double bonds. Well, it's not just a heptadiendiol. Clearly, it's got a chlorine on it, and it's got a 1, 2, 3, 4, 5 carbon unit. That is really isopentyl, right? It's got 5 carbons, so it's pentyl. And this group, that gem dimethyl, that CH3CH3H unit, that is called the iso group. We talked about this before, and since there are 5 carbons in here, that's isopentyl. So again, this is isopropyl, this is isobutyl, so isopropyl, so iso because of this, pro because it's got 3 carbons. Isobutyl, iso because of this, butyl because there are 1, 2, 3, 4 carbons. And as in this case, this species would be isopentyl. Right? So iso, 1, 2, 3, 4, 5 carbons. It's isopentyl. And again, remember, we use iso, we use the letter I in iso in alphabetization. We use iso and sec. Well, we use iso and sec. We don't use tert in alphabetization. Iso, but not second tert. So we've got C for chloro, I for iso. So this is a chloro isopentyl heptadiendiol. Right, so what we need now is locants, and again, major functional groups are the hydroxy groups, so we're going to number those right to left, so we get the lower locants. So this becomes 1, 2, 3, 4, 5, 6, 7, and this will therefore be 6 chloro, 5 isopentyl, hepta, 3, 5 diene, 1, 2 diol. So it's 6 chloro, 5 isopentyl, hepta, 3, 5 diene, 1, 2 diol. Or 6 chloro, 5 isopentyl, 3, 5 heptadiene, 1, 2 diol. But we're not done. Whenever we have carbon-carbon double bonds, we have to worry about the possibility of cis and trans, the possibility of geometric isomerism. That's better said. So we have to worry about the possibility of geometric isomerism. And again, when will we get geometric isomerism? When neither vinylic carbon has the same 2 groups. Right? Or put another way, when both vinylic carbons have different groups on each of them. So if I look at this compound, this vinylic carbon has H and that crack, so that's a candidate. This one has H and that stuff. So neither vinylic carbon in this set, for this carbon-carbon double bond, have the same 2 groups. Therefore, there is a possibility of geometric isomerism about this carbon-carbon double bond. If I look at the other one, it's got, this carbon has chlorine and methyl, well they're different. And this carbon has this stuff, and isopentyl, so they're different. So both carbons have the potential for geometric isomerism. Okay, good. So I have to now decide which
scheme, which naming scheme for the geometric isomers do I use? Do I use cis strands? Do I use easy? And what's important is I can't mix conventions. So if I decide to use cis strands for one, I must use cis strands for the other. If I decide to use EZ for one, I must use EZ for the other. Okay, so here's what I'm going to look at. If I look at the configuration, right, and again, I remember talking about this last time, configuration deals with the permanent three-dimensional arrangement about some center. In this case, about the carbon-carbon double bond. Right? Because we can't rotate about the carbon-carbon double bond. So you're stuck. Right? Either, the chlorine and the isopentyl are stuck trans to each other. So that's a permanent three-dimensional arrangement. So if I look at this one, I have an H understood here and an H understood here. So this group is trans. From the H perspective, it's trans. Now, I can't speak to this diol group and to this thing because these are not the same. So I could call the configuration about the 3,4 double bond trans, and I could be fine with that. Okay, what about the 5,6 double bond? Well, I've got a chlorine here, but there's no chlorine on 5. There's a chlorine on 6, but not on 5. There's a methyl on 6, on carbon 6, but it's not on 5. So there is no group on carbon 6 that is repeated on carbon 5. Right? Unlike the case here where the H on carbon 4 is repeated on carbon 3. So while I can speak of trans here, right, and that would be a valid term, there is no trans or cis about the 5,6 bond. Right? Because I don't have the same group on opposite sides of the double bond, or on the same side for that matter, on the adjacent carbons. So the cis-trans label doesn't apply here. So if it doesn't apply, although it applies here, I can't use the trans names, the cis-trans names to describe this compound. Because I can't use trans with this one and EZ with that one. I mean, that doesn't, you can't mix conventions. So it means we're locked in to using EZ for both. So I'm going to have to go to this one and ask, is it E or is it Z? Well, obviously, on this carbon, right, carbon beats H. So this is priority 1, that's priority 2. On this carbon, carbon beats H. So this is priority 1, and this is priority 2. So the groups of like priority, 2 and 2, or 1 and 1, right, are on opposite sides. So this side is E. Okay, then on this one, chlorine has a higher atomic number than carbon. So this is priority 1, that's priority 2. On this one, I've got carbon and I've got this. Now, this brings us to a very interesting little point. So when remember we talked about the first point of difference in determining your priority, right? So your first point of difference is based upon the atomic number of the atoms. And the higher the atomic number, the higher the priority. Or if they've got the same atomic number, like isotopes, then it would be the high atomic mass would work. Now, if I have, for example, a carbon-carbon double bond, which I do in that case, and I want to determine priorities, or let's say I have a carbon-carbon triple bond, and I want to determine priorities, or I've got a carbon-nitrogen triple bond, how do I determine the relative priorities of these species? So here's what I do. So here's the point of attachment. Well, the way I look at a carbon-carbon double bond, the way I look at pi bonds, and it's kind of hard to describe, we're going to imagine just for the purpose of nomenclature, this is not real, we're going to imagine that we're going to basically say, I'm going to cleave the carbon-carbon bond. I'm going to imagine it being cleaved. So I'm going to break it, I'm going to split it, and I'm going to seal the wound with whatever atom they were each attached to. So this will become C and H, that hasn't changed. The sigma bond remains intact, that hasn't changed. But when I sort of lyse the carbon-carbon bond, this carbon was attached to a carbon, and then this carbon was attached to another carbon. So let's put another carbon here. Okay? And let's say there were H's on this one. Let's leave those H's on. What about here? Well, there are 2 pi bonds. So in this system, I would have had carbon attached to carbon. That's my sigma bond. But for every pi bond that I split, I'm going to backfill with whatever the carbon was attached to before I split them. So for the first one, this carbon would have been attached to a C. So with this one is attached to this is also attached to the second pi bond. It'll be a C and then a C. And if I had an H here, for example, that would remain. For a triple bond N, the C triple bond N, this would equate to C, N, 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 C, C. Now, we're not in any way suggesting that this is the structure of the species. This is just a made-up way to figure out how to name them. In fact, the whole naming thing is made up anyway, right? But it's what we agree on. That is the IUPAC protocol. So this was agreed upon long before I started organic chemistry, although it is refined every couple of years. So what that means then is if I look at carbon 5 and I want to determine priorities, this carbon is attached to a 1 carbon. This carbon is attached to 1 carbon. So far, they're attached to a carbon each, right? They're attached to a carbon each. Whereas this carbon is attached to another carbon, because if these are the same at this point, I need to go 1 atom out. Well, 1 atom out here is another carbon. But according to convention, 1 atom out from this is 2 carbons. 1 here and 1 here. Right? So the way you treat a double bond is that this carbon really feels like it's attached to 2 carbons. And if you look at it then, on this carbon I have H, H, C. On this one, technically I have H, C, C. So the H's are a wash, but C, and I've got a carbon here, which is one of the carbons here is a wash. So I've got H, that's fine. C, and then one of these C's, that's fine. But then whereas this has another H, that has another C. So C double bond C beats C single bond C. And as you might interpret, C triple bond C beats C double bond C and C single bond C. C triple bond N would beat them all, because so carbon is equivalent to carbon, but the N's have a higher atomic number than the carbons. So the N's beat carbon, right? You know, if I had a carbonyl group C double bond O, that would essentially be CO O C, right? That's what that would look like. All of this to say, when I look at this system, this is first priority and that is second. So here my groups of like priority, 1 and 1 are on the same side, and so this side will be Z. So I would call this compound one was E. So this one was E, and this one is Z. So I would call that comma, 5Z, 6-chloro, 5-isopentyl, hepta 3,5-diene, a 1,2-diol. Okay? And the way we typically do these is you want the smaller number first. So 3 would beat 5. So we say 3E, comma 5Z, in parentheses, 6-chloro, blah, 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 blah. Okay. So alkanes, alkenes, alkynes. Alkanes, alkenes, alkynes, haloalkanes, alcohols. Let's do an ether. So how do we name ethers? So we name ethers as alkoxy alkanes. And let me just remind you of what an ether looks like. So ethers are R-O-R. And I'll write R prime to indicate that the R groups may not be the same. These have to be alkyl. So if I have this compound, so they're named as alkoxy, alk something, Ne. So this could be A, E, or Y, depending on the backbone. So they're called alkoxy alkanes, right? Just to make a quick point here, OH, the OH group, is called a hydroxy group. So OR, instead of hydrogen, I've got alkyl, so that's called an alkoxy group. So in a case like this, so they're called alkoxy alkanes. So the first thing I'll write is ANE. In this case, I've got methyl. So this is a methane. And the group is methoxy. So this compound is methoxymethane. What if I had this compound? Okay. Well, again, that's an ether. So it's an alkoxy alkane. So I'm going to write ane. I'm going to look at the group that has the most carbons in it. And I'm going to call that, I'm going to use that for the base. So this is 1, 2, 3, 4, 1, 2, 3, 4. So it's bute. So this is a butane. And this group that's on the butane is an isopropoxy. Right? So it's got 3 carbons, so it's an alkyl group.